I heard this question many times. After I compress a file, for example, after I zip it, can I compress it again to make it even smaller? And what if I repeat that over and over again? Will that file become even smaller? And what if my compression algorithm is really, really good? Can I achieve a compression which results in a file which is just 1 bit long? Well, the answer to that is it depends, and I'd like to show you why. And this will lead us to an interesting discovery that some compressed file can actually become bigger than the original file. And there's nothing that any compression algorithm can do about it, no matter how good it is. To be clear, we're talking about lossless compression algorithms, which means that from the compressed file, you can reconstruct the original file without any loss of accuracy. So this is in contrast with lossy algorithms where, yes, the file size goes down, but quality degrades too. This is typically used for images, for example. So to begin with, let's take a look at the idea behind the algorithm for zip files. We'll not look exactly at how it works in detail because there's more than one single algorithm and the details are not too important for now. But I'd like to give you the intuition about it at least. So first, let's clearly define our actors here. We have a file. Okay, this is our input file that we want to compress. We give this file to a compressor. This is a computer program. It's an algorithm that will take our input file and compress it. So the compressor outputs the smaller file here. We can then, if we want to reconstruct the original file, we will give the smaller file to the decompressor, which is another computer program which is tightly linked to the compressor. Okay, and the decompressor will produce again the original file unchanged. Okay, so let's go right in with an example. Let's say we have this input file here. It's a short string of text, a quite meaningless sentence, but it doesn't matter. Now, say we wanted to compress it. What can we do? I'll write the compressed version underneath here. Well, we start without any ideas, right? So I'll just start writing the compressed file down here, word by word, just like the original file. But then we reach this word here, disagreement. This word is in a way special. And the reason it is special is that we already seen this word, or at least this sequence of characters here, right? So what if instead of rewriting it as is, we just annotate that this is identical to something that we've already seen? If you think about the decompressor as another person, when they reach this point in the text, we could tell them, hey, you don't have to, I won't tell you what the next word is, but I will tell you that it is the same as this particular previous word. We just need to provide the coordinates of the previous word. So if we can do that, if we can provide those coordinates in less space that it would take to rewrite the original word, then we would have achieved some level of compression. Okay. As our coordinates, we can use two values. One value would be how many characters back we can find this word. In this case, this is 14 letters back plus 1. If you see, the space is also in common, so we can put 15 here. And then the second coordinate is how many characters the word is long. In our case, disagreement is 12 characters long, but we also include the space, so we put here 13. Okay, and we write it like this. I added some square brackets too, which serve as an indication for the decompressor to delimit the parts of the file that should be interpreted as coordinates and not copied as they were. Okay, we keep doing this, and you can see that the final text is going to be shorter than the initial one, but we didn't lose any information, right? As long as the decompressor knows what to do with those numbers that we put in square brackets, she can reconstruct the original file. Now, in reality, a compression algorithm would work on the binary representation of the input text, not on the characters themselves, but that's fine. The idea doesn't change at all. If anything, when working with the binary representation, there's more chance of finding duplicate chunks, stuff that we can represent with coordinates, and the coordinates themselves will even take less space. So, which means even higher compression ratios. Okay, so now I'm thinking, okay, but how does that answer the question from the beginning? Well, let's think about it. We want to compress it over and over again, right? But if I already compress it once, this means that all the duplicate words are gone. So my only chance here is if I can find some duplicate coordinates. Now we treat coordinates as data. So if I can find duplicate coordinates, I can compress that. I can compress those, but the chance is very unlikely, even though it's possible. And with large files, you may be able to squeeze something out, but this process needs to have a limit, right? At some point, you would have just squeezed out all the duplication there is. But what if I really want to go down to 1 bit? What are my options here? Clearly, I cannot compress it over and over again, but what if I use a different compression algorithm? Imagine this. We have 2 binary files and we build a compression algorithm that just looks like this. So here are our files. We have document A looks like this. Document B, it's a completely different document. We're looking at them in binary. And our compression algorithm works like this. Document A, we declare it is going to be compressed as 0. And document B, we declare it's going to be compressed as 1. Have we just compressed a potentially long file, maybe a whole movie, down to 1 bit? Well, with this compression algorithm, effectively, yes. The question is, at what cost? Because you see, now your decompressor must be huge, because to decompress this file, so if the decompressor got a 0 here, to decompress it into the original file, the decompressor needs to have the original file. This doesn't just happen in this extreme case. Clearly, this is a completely unrealistic example. But there's a general principle here. The more complex your compressor is in terms of even algorithm, and the higher compression ratios it will achieve, but the more complex your decompressor will need to be to reconstruct the original file, and thus more space the decompressor will occupy on disk. Okay, even if it doesn't physically contain copies of the original file, that's the same. The complexity of the algorithm makes it increase in size. And what happens to all the other files, which are different from document A and document B, right? We haven't talked about them. We haven't considered them in this algorithm. There are different options, but there is something that we can say for sure. If our compressor algorithm tries to compress something else, there might be the case that the output, the compressed file, is actually gonna be bigger than the original. And this doesn't just happen for this specific algorithm. This happens for all of them. Every possible algorithm that we can conceive. So I will repeat, in all lossless compression algorithms, meaning we don't want to degrade the quality of the file, some files will become bigger after being compressed. To understand why, let's put our hands on all possible input files up to a certain size. Okay, to keep it simple, let's limit ourselves to 3-bit maximum. So I will write here all the files which go from 1 bit, 2 bits, 3 bits. This is the list of all the possible files that you can build with a maximum of 3 bits. Okay, let's say that these are our input files. So we don't know what our compression algorithm is, but there is something we know. We know that it must map input files with output compressed files. And of course, since we are compressing things, we want the outputs to be smaller than the inputs. There is something else that we know. We know that the compressor cannot produce the same output for 2 different input files. If it would, then the decompressor would have no way of knowing which original file a compressed file corresponded to, right? Okay, then let's start assigning which compressed file goes with which input file. The specific choice doesn't matter. This is just an example, but as long as the compressed file is smaller than the input, we are fine. It's a conceivable compression algorithm. These two on top are easy. 0, we can not really compress it to down to 0 bits, right? So we'll just keep it unchanged, 0, and this one to 1. Now on the bottom though, we have a 3-bit input file, and we can definitely compress it down to 2 bits, for example. So we can have 0, 0 here, and again, similar for this one, 0, 1, 1, 0, and 1, 1. We find a problem here though. Again, we have a 3-bit input file, and we'd like the output to be 2 bits, but we finished all of our possible 2-bit files. We cannot use any other 2-bit file, because if we repeat one of the ones we already used, then the decompressor will not be able to know which one was the input file, right? We create some ambiguity. Okay, no big deal. I guess we'll just keep the file size the same. It's not ideal, but better than nothing. So maybe we can just repeat here 0, 1, 1, 0, 1, 0. Again, not really compressing, but 0, 0, 1, 0, 0, 0. But you see where this is going. Now our input file is made up by 2-bit, it's 2-bit longs. And we cannot use any 1-bit file, output file, because we already used all of them. We cannot use any 2-bit output file because we already used all of them. This means that we must produce a 3-bit output file. We haven't used this one, 1, 0, 0, we haven't used it, 1, 0, 1, 1, 1, 0, and 1, 1, 1. So look at this. We have some input files that when compressed become bigger than they were. Now we just chose an example with 3 bits, but you can easily prove that this happens for every number of bits. And did you notice that we didn't make any assumption about the compression algorithm? This means that this must happen for all compression algorithms. For all compression algorithms, there must be some files which become smaller and some files which actually become bigger when compressed. This includes our algorithm from the beginning, even though it might not be immediately clear why. Let me know in the comments if you can figure out why. So what should a smart compression algorithm do? Well, a smart algorithm would need to ensure that for the average file content, for those file types that are common, that are more likely to exist in the real world, the output becomes smaller. And for all the unlikely file contents, those files which is extremely rare to see in practice, For those files, we can produce a bigger output because most likely nobody will ever notice. Okay, so let's see if this is true. Let's put it to the test. What's the most unlikely file content that we can think of? Maybe a totally random file. I mean, totally random bits of content. It is meaningless. It's the literal definition of meaningless. Okay, so let's try it. I'm generating a random file of 1 kilobyte. Then I'm compressing it. And you can see that the output is actually bigger. A compressed file is bigger than the original, as expected. I hope you gained a slightly better understanding of how data compression algorithms work, and most importantly, what are the limitations about them. This is a very fascinating topic. There is so much more about it. I will add some reference in the description of the video in case you want to read more about the science behind it.